In this video, I'll be talking about conservation of energy in an electric field. If you have a charged particle in an electric field and the total energy of the charged particle in that field is always constant, it cannot change. Or in other words, the total energy for an isolated system is always constant. You cannot create energy, you cannot destroy energy. What you can simply do is change the energy from one form of energy to another form of energy. In this case, mostly from kinetic energy to electric potential energy. So there's always change from one energy to another energy, and you cannot create energy. Now let's talk about this specific case in this one example here. Let's say you have one positive plate and then a negative plate here. That means you have a uniform electric field, because the electric field between a positive plate and negative plate is uniform. And then you have a charged particle. Let's say this positive charged particle, and this positive charged particle has a velocity at this point. Okay, and if you want to understand in this exactly in terms of the gravitational field, what you can imagine, let's say this is the ground, and then you have a mass here, and this mass is moving downwards with the velocity va or vb. Okay, and we are interested in finding out in this case what is the velocity of the particle when it hits the negative plate here. And you see this the negative charge will attract this charge here, will attract. That means the velocity will increase. When the velocity increases, that means the kinetic energy increases. That means the potential energy must decrease in order to maintain the total energy at a constant level. So it's just again the what is changing here. So at this point, this charged particle has the total has both kinetic energy and the potential energy. When you release this charged particle, all the energy now will be changing into the kinetic energy. So let's write down the equation. So what do we have? Assuming, let's call this as the initial kinetic energy, and this is the final. This is the total initial energy here, and the total final energy here. These two energy has to be equal. That's what this equation tells you. The kinetic energy plus potential energy, the initial total energy has to be equal to the total energy, or total initial total final kinetic energy plus potential energy. As this particle is moving at this point, it does have some energy or kinetic energy, and that is given by half m, the mass time velocity squared. And this mass is the mass of the charged particle. Charged particle. And the potential energy of this charged particle is equal to the charge times the potential at this point. What is the potential at this point? The potential at this point, we call this potential as a VB potential, and this potential is VA potential. Or that means this plate is at, let's say, maybe like 100 volt, and this could be, let's say, minus 25 volt or minus 100 volt. It could be any voltage. So that's what the voltage is here. And now when the particle reaches at this point, then we assume the velocity of that particle or the charged particle at that point is VA, and the potential energy at this point is Q times VA. Okay. So this is the conservation of energy equation. And now let's call a special case here. When I say special case, let's say this charged particle is at rest. Even if it is at rest, this negative plate will attract it. So the particle, the charged particle, this positive particle will start moving towards this negative plate. So now let's write down that equation. So in this case, if the charged particle is at rest, the initial kinetic energy is 0. And again, everything remains the same. This is the potential energy, and this is the kinetic energy, and at this point this is the potential energy. Now we can solve for this velocity here. If we solve for the velocity, this is the equation we get here. And remember, this V, this straight V stands for the potential, and this italic V stands for the velocity. In all lectures, just remember this one. This V stands for the potential, and this V stands for the velocity. As you can see, this is the potential and this is the velocity. This is the velocity and this is the potential. So just make a distinction between those two. Do not get confused by the velocity and the potential, as we denote both by the same notation but in different style. So this is it for the conservation of energy.